Work is the means by which energy is transferred from one body to another. You can find it numerically by taking the force multiplied by the distance. Now, what do we mean by the force multiplied by the distance? This is the force that's actually applied to a body, and the distance is the distance through which that body moves due to that applied force. Now, I started out by saying that work is the means by which energy is transferred from one body to another. Okay, I have energy, and I got my energy from the sun. My energy can be put into this bow by applying force on it. Okay, so when I pull back on the string like this, I'm exerting a force. You can see the movement of the body. So now this bow possesses energy. The type of energy could be described as elastic potential energy. But now this bow in this state is capable of doing work on this arrow. Okay, so I pulled it back. The bow possesses energy, elastic potential energy. By the bow doing work on the arrow, it transfers its energy in the form of elastic potential energy into the energy of the arrow, which is kinetic energy. When I wind up this toy, I'm exerting a force over a distance. So I'm putting energy into this toy, and it's being stored as elastic potential energy. Then inside this toy, work is done to take that elastic potential energy and transfer it into energy of motion, kinetic energy, and sound energy. This flashlight is called a shake flashlight. If I do work on it, exerting a force over a distance, it's stored as electric potential energy, and then I can have this mechanism do work and convert it into light energy, as you can see. Here's one of my toy trains. I'm going to hook it up to this device. And what this device does is it takes energy from me via work and converts it into electric energy. And the electric energy then goes into this train. And then the train converts that electric energy into kinetic energy. Okay, let's see. Okay, this piece of equipment here is called a generator. And what a generator does is it converts one form of energy, mechanical energy, this is called, because there's motion, into electrical energy. Okay, here's another generator, and I do work, so it takes my energy, the generator converts it into electrical energy, it lights. Sound energy. Of course, there's also some kinetic energy there too, because there's a little hammer going back and forth hitting the bells. Now, you'll notice that if I unscrew this light bulb, it becomes a lot easier to turn this. So I screw the light bulb in, it's a lot harder to turn it. You can't get something for nothing. There's no such thing as a free lunch. Okay, let's return to this mathematical equation here. We can represent work with a W, force with a capital F, and distance with D. The unit of force is the Newton, the unit of distance is the meter, and the unit of work is the Newton meter, which is also called a joule in honor of James Prescott Joule. So 1 joule is equal to 1 Newton meter. Power. Power is equal to the work done divided by the time. You already know the symbol for work, W, symbol for time, T. The symbol for power is P. The unit, well, work is the joule, time is the second, so power is the joule per second, also known as the watt. Does anyone know? That's right, the watt, which use the symbol W for that. Don't confuse it for the symbol for work, which is also W. Now you're going to be doing an activity where you're going to be determining your power not only in watts but also horsepower, which is kind of an archaic unit of power if you think about it, because horses. Okay, so dawn of the automobile, they compared the power of automobiles to horses, because that was the original form of moving cars around, carriages. Okay, the next thing I want to talk about is a form of energy called potential energy. And in particular, we're going to talk about gravitational potential energy in this unit. Gravitational potential energy is equal to weight times height. Or W times H. Gravitational potential energy we can represent with PE, okay? Now weight, we learned in a previous unit, can be found by taking the mass of the object times the acceleration due to gravity. The unit of potential energy is the joule, just like work. Now think about why that is. Well, remember I said work is the means by which energy is transferred from one object to another. So when I lift this apple, I'm exerting a force upward, which is equal to the weight of the apple over a distance h. So when it's in this position here, it has a potential energy equal to mgh. Now, I can show you, prove to you that it has energy, because upon release, notice it gains energy of motion, which is called kinetic energy. And then of course, then that energy is transferred into the table, which causes the table to shake, and you got that sound when it hit the table. The next form of energy that I'd like to talk about is kinetic energy. Okay, so then that will conclude our two types of energy that we'll be studying in this chapter: potential energy and kinetic energy. Potential energy is sometimes referred to as energy of position. Kinetic energy is energy of motion. it's equal to 1/2 the mass of the body that has the kinetic energy times the speed of the body squared. There's an interesting history behind that equation. Newton originally thought of energy, kinetic energy, as just V times m rather than V squared. And you'll learn a little bit more about that later, or if you already did the reading, you learned about that. So let's go back to this bow and arrow demonstration. So I'm going to do work pulling the arrow back. And then the bow, in turn, so now there's potential energy in here, elastic potential energy, which we're not going to be focusing on in this chapter. We'll talk a little bit about it like now. We're mainly going to study gravitational potential energy. But there's an elastic potential energy in here. And when I release this, the bow does work on the arrow. And the energy is converted into energy of motion. The elastic potential energy is converted into energy of motion, which we call kinetic energy. And we'll be doing an activity in the future using the bow and arrow. Now, the relationship between work and kinetic energy is known as the work-kinetic energy theorem. And it states that the work is equal to the change in kinetic energy. So you would have 1/2 mvf squared minus 1/2 mvo squared. Now, I failed to show you how to abbreviate kinetic energy, so let me just do that. It's KE. So the work kinetic energy theorem can be written as W is equal to delta KE. Now, going back to that bow and arrow, did you notice that it started out with 0 kinetic energy, right? Because the arrow was at rest. The bow did work on it and gave it kinetic energy, final kinetic energy. Suppose a car is driving along the road at an unknown speed, and it applies the brakes and skids to a stop. And let's say the car leaves skid marks on the road. And we measure those skid marks. And we'll call the length of the skid marks D. And let's say we want to know how fast the car was traveling just before applying the brakes. Why? Because we want to know whether this car was speeding. Okay, so here it's traveling along at an unknown speed. Here, it's at rest. So how can we figure out this unknown speed? Well, we can use the work kinetic energy theorem. The work done in stopping the car is equal to the change in kinetic energy of the car. Now, what does the work on the car to stop it? What force is being applied to the car over the distance it moves until it stops? Friction. So the road is exerting that force. So there's a force of friction that acts from the moment it brakes to the moment it stops. If it skids, what kind of friction is it? Kinetic friction, right? Remember, that's also known as sliding friction. FK. Now, recall we learned something interesting about kinetic friction. It tends to be independent of speed. So if you're doing an accident investigation, you want to know whether this car was speeding or not, you can assume that the force of kinetic friction is relatively constant. So Fk is what's doing the work over a distance d. And since they're oppositely directed, I'm going to throw a negative sign in front of the Fk. That's equal to the change in kinetic energy. So we have 1/2 mv F squared, well that's 0, minus 1/2 mv O squared. The negative signs cancel out because they appear on both sides. We know the distance. We don't know the mass, but if we solve for VO, the speed, we can see that the speed is equal to the square root of Fkd times 2 over the mass. Okay? Now, there are ways of figuring out Fk. They use what's called a drag sled. Okay, we're not going to get into that. Okay, but basically, police, they put a box on the road, and underneath the box, they put a part of the car's tire, something similar, and they pull it with a spring scale, they read the force. Okay, so then they know the force of kinetic friction on that box. Knowing the weight of the box, okay, they can use an equation which will give you the coefficient of kinetic friction between the tires of the car and the road. And that characterizes the interface between the car tires and the road, and that remains a constant. Once they know that, they can apply that to the car itself. So the kinetic friction that acts on the car then is equal to this coefficient that we figured out using the drag sled multiplied by the normal force or the weight of the car. Now what's interesting is since weight is m times g, the mass of the car gets canceled out. So what you end up with is that the speed is equal to basically the square root of 2 times this coefficient thingy that I talked about, which you don't really need to know about in this course. Okay, we use the Greek letter mu subscript k, so it's called the coefficient of kinetic friction. Masses cancel out. You have g and you have d remaining. So the square root of 2 uk gd. Now, the other thing I want to point out here is how does the stopping distance relate to the speed of the car before it's braking? And if you go back to this equation here, VO is equal to the square root of 2fkd over m, or even this equation, can you see the relationship? Okay, so what I'm going to do here is I'm going to square both sides. So if I square both sides of this equation, I get VO squared is equal to 2 uk gd. What this tells us is that the stopping distance is proportional to the square of the speed. So suppose this car was traveling, let's say at 20 miles per hour. We'll use British, now we use English type units. They're not the British engineering, that would be feet per second. So let's say that it's traveling at 20 miles per hour, and let's say it skids 50 feet. Now suppose instead of 20 miles per hour, the car doubles its speed, and it's going 40 miles per hour. Now what would the stopping speed be? Now remember, the force of kinetic friction is independent of speed. So we doubled the speed, but we would have to quadruple, right, because the speed is squared, the stopping distance. So if it took 50 feet to stop at 20 miles per hour, it would take what to stop at 40 miles per hour? Maybe 100 feet, 300 feet? Well, take 50 times 4. That's right, 200 feet. Right, so instead of 20 feet, or 50 feet to stop, it would take 200 feet to stop. Okay? So if you double the speed of a car, the stopping distance quadruples. How much work did I do in carrying that spool across the room? Now, did you notice that I was walking at a constant speed? Well, if you go back to the definition of work, force times distance, remember that the force that acts on the body doing the work causes the body to move a distance d. But the force I exert on this, if I'm walking at a constant speed, is straight upward, is it not? Because once this body is in motion, traveling at a constant speed, it doesn't require any force to the left or to the right. So the only force that I exert on the spool is up while I'm walking at a constant speed. And then in addition to that, of course, there's a force down, the force of gravity. So the amount of work that I did on that spool in walking across the room actually turns out to be zero. Now another way of looking at that is with the work kinetic energy theorem. Notice that the kinetic energy didn't change, which means the work done is zero. How about a satellite orbiting the Earth? How much work does the force of gravity do on the satellite? And we're going to assume a circular orbit. Well, the force of gravity always acts toward the center of the Earth. Okay. Weight of the satellite, you can think of that. But the satellite is moving at this instant in that direction, tangent to the circle. So do you see that this force does not do work on the satellite, right? Because it's perpendicular. And that's why the satellite can maintain a constant speed, because its change in kinetic energy is zero. Now it's different if it's an elliptical orbit. And we'll take a look at that in a future unit. The next thing I would like to discuss is conservation of mechanical energy. In the absence of friction, mechanical or any external influences, mechanical energy is conserved. So whatever a body starts out with as far as its mechanical energy, which would be its gravitational potential energy and its kinetic energy, if you add those two together, that value should remain constant. So we say PEO, original potential energy, plus original kinetic energy, is equal to final potential energy plus final kinetic energy. Now, a classic illustration of using this is, or applying this, is the roller coaster. So suppose we have a roller coaster that looks something like this, and let's say the coaster car is traveling at, let's say, 5 meters per second here. And let's say the height of this hill is 20 meters. And let's say we want to know what its speed is when it's over here. Now this hill is measured to the ground level, and that's the level the coaster is at over here. So how fast is it traveling over here? call that VF. So, the kind of energy it starts out with is potential energy and kinetic energy. So we have, do this in yellow. So we start out here with mgh, which is 20 meters. Okay, let me make g 10 meters per second squared right away. Plus 1/2 the mass of the coaster times the original speed of the coaster, which is 5 meters per second squared, equals potential energy here is 0, right? Because it's not going any lower than this. The height is 0. The kinetic energy would be 1/2 m times the unknown speed squared. Now you notice that mass appears in each term, so that gets kicked out of town. So we're left with the following. 20 times 10 plus 1/2 times 5 squared equals 1/2 VF squared. Now if I multiply through by 2, I get 40 times 10 plus 5 squared equals VF squared. 40 times 10 is 400. 5 squared is 25. That's equal to VF squared. 400 plus 25 is 425. So VF squared is equal to 425. Take the square root of both sides. Let me put that up here. So we get that VF is equal to the square root of 425. So why don't you figure that out? And that would be the speed of the coaster here. Now let's say we want to figure out the speed of the coaster at this location here. So we know, let's say the height is, let's say 15 meters. 15 meters. And we want to know how fast the coaster is traveling at the top of this hill. Oops. All right, so we have potential energy. Oh, and this was traveling at 5 meters per second. So we have potential energy, mg, which is 10 meters per second squared, times the height, 20 meters, plus 1/2 mass times 5 meters per second squared, equals potential energy, m times 10 meters per second squared, it's right here, plus times the height, 15 meters, plus 1/2 the mass times VF squared. Okay, but this is the final speed now at the top of this hill. So let me show the coaster here. VF. So again, the mass cancels. And now we need to solve for VF squared. And I'll do that up here. So let's see, we have 10 times 20, 200, plus 25 times 1/2 equals 10 times 15, 150, plus 1/2 VF squared. I'm going to multiply through by 2, so I get 400 plus 25 equals 150 times 2, 300, plus VF squared. So 400 plus 25 is 425. Subtract 300 from both sides. So 425 minus 300 is 125. That's equal to VF squared. So VF is the square root of 125. And I'll let you do that. Figure out what the speed of the coaster is at the top of the second hill.